Before we talk about pixels, look at the whole vision machine. A photo enters on the left, signals race through the middle, and a decision appears on the right. For a computer, the photo first becomes numbers, pixels that can enter the input frame. Those numbers are not the answer yet. They are only the raw material for the architecture. The real question is, how does this path turn numbers into meaning? The orange route shows one possible answer moving through the network. Every layer transforms the signal: pixels, edges, parts, and finally an object. This is the map we will use for the whole film. Every digital image is made of tiny squares called pixels. Each pixel is just a number, brightness from 0 to 255. Color images have 3 channels: red, green, and blue. A simple photo might have millions of these numbers. To us, it's a face, a sunset, a dog. To a computer, it's just a massive grid of numbers. The challenge: find meaning in this ocean of data. This is where neural networks come in. Now let's slow down and look inside this same architecture. A realistic vision network has input gates, patch blocks, feature blocks, attention, and output scores. First, pixel values enter the left input frame as numbers from 0 to 1. These values represent brightness. That's all the network sees. Between the blocks, the wires carry weights, numbers that scale the signal. Positive weights amplify, negative weights inhibit. Each neuron multiplies its inputs by weights, sums them up, and adds a bias. Then an activation function decides: pass the signal or block it. ReLU is the most common. Positives pass, negatives become 0. Deeper blocks repeat the same process: multiply, sum, activate, and pass forward. In the middle, simple edges become textures, parts, and object clues. Finally, the right output frame uses softmax to produce probabilities. 92% confident. It's a cat. This complete trip from pixels to prediction is called the forward pass. The secret weapon of neural networks is called convolution. Imagine looking at a photo through a tiny magnifying glass. That magnifying glass is only 3 by 3 pixels, a tiny filter. It slides across the entire image, one small step at a time. At each position, it performs a simple calculation. It multiplies each pixel by the matching number in the filter, then adds all 9 results into one single output number. Let's watch this calculation happen step by step. Here's a 3 by 3 image patch, and here's our filter. We multiply each pair of numbers together, add them all up. That single sum is our output value. Slide the filter one step over, repeat. A map takes shape. Each position produces one number in the output. Now here's where convolution gets truly powerful. Different filters detect different things. This one finds vertical edges. This filter responds strongly to horizontal lines. And this one picks up corners and curves. Together, these filters capture the building blocks of vision. The first layers in the network detect the simplest features. Just edges and basic textures, nothing fancy yet. But something magical happens in the deeper layers. Edges start combining into recognizable shapes. Squares, circles, curves, geometric building blocks. Then shapes combine into real-world parts. Eyes, noses, wheels, ears, things we can recognize. And parts combine into complete objects. This hierarchy is remarkably similar to your own brain. Your visual cortex processes images the exact same way. From simple edges to complex understanding, layer by layer. Let's trace a photo through the entire pipeline. Raw pixels enter. The first layer finds edges everywhere. The next layer groups edges into textures and shapes. Deeper layers recognize familiar parts like eyes and fur. The final layer puts it all together. That's a dog. All of this happens in less than 50 milliseconds. How does a neural network learn to see? It starts with completely random filters, seeing nothing useful. Like tuning a radio blindfolded, pure static at first. You show the network thousands of labeled images. Each image has a correct answer: cat, dog, car, bird. The network makes its best guess with current filters. Then it checks, was I right or was I wrong? When it's wrong, something remarkable happens. The error is traced backwards through every single layer. This process is called backpropagation, the learning engine. Each weight gets a tiny nudge in the right direction. The filters adjust slightly to reduce the mistake. Show another image, predict, check, adjust, repeat. After thousands of images, patterns start to emerge. After millions, the network has truly learned to see. The loss curve tracks progress. Error drops over time. Each dip means less confusion, more accuracy. Gradually, random noise transforms into powerful vision. Between layers, there's a crucial step called activation. Without it, the network could only learn straight-line patterns. Imagine trying to draw a circle using only a ruler. Impossible. That's a network without activation, limited to straight lines. The most popular activation function is called ReLU. Its rule is beautifully simple. Keep positives, zero out negatives. If the signal is positive, it passes through unchanged. If negative, it's blocked, set to zero, gone. This simple rule gives the network incredible power. It introduces nonlinearity, the ability to learn any curve. Without activation, only straight decision boundaries. With activation, the network can model any shape imaginable. Spirals, circles, and complex regions all become possible. That's why ReLU appears in nearly every modern network. A beautifully simple function that unlocks infinite complexity. Images are huge, millions of pixels to process. That's way too much data for efficient computation. The solution is called pooling. Shrink data intelligently. The most common type is max pooling. It divides the image into small regions, usually 2 by 2. From each region, it keeps only the maximum value. The strongest signal survives, the rest are discarded. This cuts the data size by 75%. Think of it like stepping back from a detailed painting. You lose tiny brush strokes, but the big picture becomes clearer. Pooling also makes the network more robust. If the cat shifts a few pixels, the answer stays the same. Small changes in position don't fool the network anymore. 4 times faster, half the memory, better generalization. That's pooling, simple, effective, essential. Modern neural networks can be incredibly deep. Some have hundreds of layers stacked on each other. In 2012, AlexNet had only 8 layers and changed everything. It crushed the competition in image recognition. 2 years later, VGG pushed deeper. 19 layers. Then ResNet shocked everyone in 2015, 152 layers. Its secret: skip connections that help information flow. Without them, very deep networks simply cannot learn. Gradients vanish before reaching the early layers. Skip connections create express highways for learning. Then in 2020, vision transformers arrived. Instead of fixed filters, they use attention mechanisms. The network learns to focus on the most important parts. The deeper the network, the more abstract the understanding. From pixels to concepts, that's the power of depth.
Neural networks now see better than humans in many tasks. Medical imaging, detecting cancer earlier than doctors. Self-driving cars, understanding the road in real time. Face recognition, unlocking your phone in milliseconds. Satellite imagery, monitoring forests and climate change. Art generation, creating images from text descriptions. Quality control, finding defects in manufacturing. The applications are growing every day. From pixels to understanding, that's how neural networks see. Layers of filters extracting increasingly complex features. Trained on millions of images through backpropagation. Convolution finds patterns, pooling compresses, activation adds power. Today, these networks rival human vision. The future of machine vision is just beginning.